Okay. Unit 4, chemical reactions, calculations. There's going to be a lot of calculations in this unit. This is by far the most longest unit. This is our longest unit in the textbook. Okay, we may run over into lab. The lab today isn't very lengthy, but we may run over a little bit because it's going to be a pretty lengthy lecture, and we will be doing a few examples from the lab today anyway, so I think that'll work out just fine. Is that we'll get some examples of the reactions that we're working with, get familiar with them. I think there's 10 reactions we have to write out, and I'll get you started on a few of them. We will, so everybody should have a few examples to go off of. That way you can complete the lab. But again, there's a lot of calculations. Have your calculators ready. I am going to be calling on people. And a lot of concepts in this unit. Okay, but spend some extra time this week on this unit in particular. It will make units 5 and unit 6 much easier to understand if you can comprehend most, if not all, of what's in this unit, right? So if you're struggling with this unit, next week is going to be more difficult when we have to cover units 5 and 6. Okay, so this is kind of our foundation leading into those other 2 units, but definitely a lot of calculations and a lot of concepts, a lot of definitions in unit 4. So let's kind of go ahead and get started here. So we're getting pretty familiar with the periodic table, where we can determine valence electrons, the number of electrons, masses. We know main group metals, transition elements, metalloids, non-metals, noble gases. We know some groups here, energy levels, configuration, orbital diagrams, and we're all learning that now. And what we've seen and talked about is atomic mass, right? So if I asked somebody in this class, I said, well, what's the atomic mass of hydrogen? What would you say? It is 1, and the periodic table would say it's right underneath 1.01 atomic mass units, right? So if I wanted to know, this is our diatomic gas, right? Hydrogen gas. If one of them weighs 1.01 atomic mass units, if I want to know the mass of this, well, what would I have to do to this number? Multiply it by 2. And our answer would be 2.02 atomic mass units. And that is the mass of this. So now we're going to start putting together molecules, ionic compounds, and just simply go into the periodic table, determine how many atoms of each one that you have, multiply it by the mass, and we can get the mass of these compounds and molecules now. So we can see here, right? So on the periodic table, right, these are our masses. This is where we got hydrogen. And depending on the periodic table, right, sometimes it's written above, like this periodic table here, we have it written above where it says 1.0079. Sometimes they go out 4 or 5 decimals, but our periodic tables we use here, and in the textbook and on the exam, we're just going to go out to 2 decimal places here. So looking at water, we can determine what the mass of water is. Right? Water has 2 hydrogens, 1 oxygen, right? We've already done the mass of the 2 hydrogens, 2.02. There's 1 oxygen, so 1 times the mass of this value. And again, this value comes from the periodic table, so we just make sure we point that out here, right? And if we go to oxygen, there it is, 16.00. So that's where we're getting that value from. And then we just simply add all those up. And we come out to 18.02 as the formula mass. Formula mass. So AMU We do have another word for it that we're going to call molar mass later. Right? It's similar, not identical. The values would be identical, but the meaning is different. Okay? So for now, we'll understand that this is to be the formula mass of that particular molecule. So let's look at another molecule. So here's another molecule. So have your calculators out. If we want to determine the formula mass for this molecule here, this is sucrose, by the way. So I'll just put the name up here. You can probably reference that later. So the molecule C12H22O11, right? So this particular molecule has 12 carbons, 22 hydrogens, and 11 oxygen atoms. So let's just make a list. We have carbon, we have hydrogen, and we have oxygen. So we're just going to set up a table, and then we're going to add all these values up once we get all the values. So carbon, what's the molar mass of, and let me get back to this here. So carbon, there's 12 of them. And what's the mass of carbon?
12.01.
12.01, and we have 22 hydrogens, so I'm going to multiply that by 1.01, and then we have oxygen where we have 11 of them, and what's the mass of oxygen? 16.00. And we're going to keep our significant figures correct here. I should put an equal sign here. 12 times 12.01, anybody do this in their head? 144.12. 22.101 is 22.22. 11 times 16, what's 11 times 16, anybody? 176, thank you. So 176. Should I leave it as 176? All right, we're going to put 176.00. So here, we're going to add these up. This comes out to be 4. This is 3. No, yeah, that's right. 3, 4, 10, 12. 3, 10, 11. Oh, this is 144. I should have lined these up a little bit better. 4 plus 2. There we go. I see that. 10, 12. Then we have 4, 5, 6. Is that right? It might be 342. I'm trying to add this in my head. 342? 342.34 what? AMU, right? Atomic mass unit. So we always have to have some unit here. The atomic mass unit of chocolate chip cookies, right? Sucrose. So, and you can do one of two things. You can either write sucrose or you can write the formula of it. To me, I don't have a preference. But this is the AMU for sucrose. So the next one we have to be a little cautious here. So this is iron 2 nitrate. Iron 2 nitrate. So I'm going to expand this because this means that the subscript out of the parenthesis means that we have 2 of these nitrates. So we have this, and we have this. So we have to add our atoms up correctly so we're not running into any issues. So we'll just kind of do, I'm going to put some arrows here. When we have this out here, right, you could do this if you want to. It's not required, but you could separate everything and count everything up. Or you could take this 2 here, and we could just multiply these together, right? So if I ask, so we have 1 iron atom here. For nitrogen, how many atoms do we have? There's an imaginary 1 here. So we simply just have 2, and that matches the 2 that we have here. And then 3 times 2 is 6, and we can see that 3 plus 3 is also 6. So we can just multiply this way. What we don't want to do is we don't want to take this and multiply it by this one out here. So this only represents what's inside of those parentheses there. And now we're going to go ahead and collect the mass of all these. So what is the mass of iron from the periodic table? So 55.85. The mass of nitrogen? 14.01. And oxygen we just did, which is 16.00. So we will just do the math on that. So one at a time I'll be at, 1 times 55.85, we don't need anything for that. For nitrogen times 2, this is 28.02. And 6 times 16, anybody? 96? Did I hear that correct?
Yeah.
So 96.00, and then we're just going to add all of these up here. So add these up, somebody, and give me that value. 165.80 what? This is 5, this is 2. $179.87. So 179.87 atomic mass units of iron to nitrate. While we're here, while I have this, you know what? No, let me. We're not. I don't think we're quite there yet. We'll get a little bit off track there. All right. So we're going to learn a new unit today. Right? We're learning a new unit that we call the mole. Right? We have units like meters, liters, grams, joules, degrees Celsius, Kelvin. Those are all units, right? Units of temperature, units of volume, length, mass. This is another unit that we call the mole. And don't be intimidated by this. I'm going to try and explain this. 6.02 times 10 to the 23 things. Literally anything. 1 mole. 1 mole is equal to 6.02 times 10 to the 23 things. It can literally be anything, nothing specific. This is a unit of how many things you have. And I'll give you some examples. If I said I have a single Great Dane at home, what would you all say? How many Great Danes do I have? 1. I never said 1 though, so how do you know that I only have 1? Oh, because I said single, and that's what single represents. Single represents 1. If I had a couple of Great Danes, how many Great Danes do I have? 2. If I have a few Great Danes, how many do I have? 3, because few means 3. And not an untrue story. I literally do have 3 Great Danes at home. They weigh about 160 to 180 pounds. They're ridiculously childish, and they've taken over the sectional in our living room. I can't even sit in the sectional. Like it belongs to them. They fill up the entire sectional. It's ridiculous. Still trying to sit in my lap. But moving on. So we know that few. So these mole is similar to that, right? If I had I don't have a dozen Great Danes. If I had a dozen Great Danes at home, how many Great Danes would I have? 12. If I had a dozen donuts, I'd have 12 donuts. If I had a few pennies, I'd have 3 pennies. If I have a couple pennies, I have 2 pennies. If I have a mole of pennies, how many pennies do I have? I have 6.02 times 10 to the 23 pennies. Right? If I had a mole of Great Danes, I would have 6.02 times 10 to the 23 Great Danes. Right? And this is how we treat this value, right? It's a specific number, a specific quantity of anything, right? Couple isn't specific to anything, right? Just it really represents just 2 things, whatever those things may be. In our case, we are going to be pretty specific. Right? Mole, or this is what we call Avogadro's number here. Avogadro's number. Right? Avogadro's number. You'll know when to use this if you see 3 keywords. If you hear or see 3 keywords, you're going to know that you need this definition. Okay, because this is a definition. Right? Is that if you're asked to determine the number of atoms, if you're asked to determine the number of molecules, or you're asked to calculate the number of particles. If you see these 3 keywords in a problem, or I ask you, is that this is when we need this definition here, right? And molecules, let's just get this straight here. Mole is not the same thing as molecules, right? Those are 2 different meanings, right? Mole, 6.02 times 10 to the 23 things. Molecules are non-metal elements that we put together, right? Sucrose is a molecule, okay? So these definitions here, right, we can turn those into conversion factors, right? We can write as 1 mole over 6.02 times 10 to the 23 things, or 6.02 times 23 things for every 1 mole. So we can answer these questions now and calculate these, right? And there's our key word. How many atoms are in 2.3 moles of sodium? Well, because I see the word atoms, I know that I'm going to need Avogadro's number. I'm going to need this definition of the number of things, right? How many molecules, right? There's another key word. If I have this many molecules, it's not asking me for molecules, right? It's asking me how many moles, but the problem, here's a key word. If you see it or if you hear this word, molecules, best get ready with Avogadro's number and that specific definition. You're gonna need that value. Okay? So how many atoms are in 2.34 moles? So when we come across word problems like this, write your information first. We talked about this during dosage calculations. Take your data first, your information that's provided to you. That's where we're going to start. Then we'll worry about converting after that, right? We don't convert first, right? Data, then we worry about converting. So the information that's given to us says that we have 2.34 moles of sodium. Now, I'm going to need to convert this, and there's two things I can do here. So I'm going to write this definition twice. I'm going to write 1 mole over 6.02 times 10 to the 23 things. Or we can write it as 6.02 times 10 to the 23 things over 1 mole. What is the things that we're asked to look for? Atoms. We're asked to look for the number of atoms. So I'm going to take this word here, things, because I know what the things are, and the things are atoms. That's what we're looking for. So I'm going to take this word here. The specific things we're looking for are atoms. So now that narrows it down a lot, because only one of these is going to work in order to cancel out the number of moles. So which one should we use? The one on the right or the left? Right? We need this one here, because I've also mentioned whatever it is that you're looking for, how many atoms, you need to do everything you can to make sure that this keyword here is in the numerator. So I know to use this one because this is what I'm looking for. So let's write that down. So we got 6.02 times 10 to the 23 atoms over 1 mole. And again, I keep throwing out the chemists, we need shortcuts for everything. This is my shorthand. This is my shorthand for this. They mean the exact same thing, right? But chemists, we're a little lazy. We just lop off the E and we just kind of forget about it sometimes. So this is the same thing. But let me write mole here. So these moles cancel out, and whatever I answer now, whatever I calculate now, is going to be the number of atoms of sodium that we have. Okay, so let's calculate. Somebody calculate this for me. 2.34 times 6.02 times 10 to the 23, and shout out the answer when you have it.
To 3.89 times 10 to the negative 24 atoms?
It would not be to the negative. If we were dividing it, we may have a negative. It's going to be this multiplied by this. But let's stay with you, Adam. So how are you? Let me see how you're putting this into your calculator.
I'll put it in upside down.
Oh yeah. So yeah, flip those around and then let me know what that answer is. And we're going to stick. Okay, yeah. So here, this is a definition. Are there any significant figures that we have to worry about in definitions? No. All right. So just our measurement, just our data. So 3 significant figures. So add up to 3 significant figures. What's our answer?
1.41 times 10 to the 24.
Times 10 to the 24 atoms of sodium. Right. So I think that's a pretty good answer. The next one, how many molecules? All right, so I guess my molecules is going to be in the numerator. And we're going to change this word here. So instead of saying atoms, we're going to change that things into molecules. I'm going to take this and change that into the word molecules. All right. And we're going to start with information that's given to us. So we're going to put, let me erase the top one here. So we have 1.54 moles of hydrochloric acid, and we need to figure out how many molecules are in there. So we need to make sure that molecules are in the numerator, so I guess we're using this one over here. So again, we put 6.02 times 10 to the 23 molecules per mole. So this gets to cancel this. And here, 1.54 times 6.02 times 1023. Somebody other than Adam calculate this.
.27 times 10 to the 23.
23 molecules hydrochloric acid. 9.27 times 10.3 molecules hydrochloric acid. So good answer there. All right. Now, our next problem here. It's not asking for molecules, it's asking for moles now. But because I see the word molecules, I still know we need Avogadro's number. We still need this particular definition. But what is the unit that we want in the numerator this time? Moles, right? If it's asking us to calculate the number of moles, we need the number of moles in the numerator. So we're going to have 2.54 times 10 to the 24 molecules hydrochloric acid, and it's asking us for moles. So we're going to need this one this time. We have 1 mole, 6.02 times 10 to the 23 molecules. So this unit cancels out this unit. And let's see what this is, 2.54. I'm going to have you calculate this with me. I do need to ask everybody a question after this. All right. So we should get 4.22 moles, and here's the question I'm going to ask because I do need to know this. This is our answer. 4 point, let me double check here. 2.54 times 10 to the 24. Okay. This answer, if you got this answer here, which is not correct, I need to know, did anybody get 4.22 times 10 to the 46? If you did get that answer, please let me know so I can come help correct this. So, did everybody else get 4.2? 4.2? Who did not get 4.2? I need to know. I need to know. I'm just gonna walk out to those that didn't. I want to make sure that we're getting this answer. Excuse me. All right. So let's see how we input this in. Oh, that's 6.03. Let me get that. Let me make one correction. 4.1. Did we get 4.1? 6.02. 2.54 times 10 to the 24 divided by 6.02 times 10 to the 23.
Yeah, it's good.
Yeah. Should do it.
4.22. Who got 4 point, anybody get 4.15? So it looks like you put it in your calculator just fine. Can you recalculate that and see?
Yeah, I got a 1.52, and I think I entered it right.
All right, so let's take a look at these. I'll get back there, Mom. Okay, so here, this is not scientific notation friendly at all.
Okay.
Anytime that you do scientific notation, you are either going to have to do one of two things here.
Yes, go on to that second row.
Let's do. How do you get? I don't know how to clear. Oh, there it is. You either use this when you're dividing by scientific notation, because what happened in your count, or you use parentheses around scientific notation, because in your calculator, this is what your calculator understood, because it's just not user friendly with scientific notation. Okay? Is that your calculator did this 2.54 times 10 to the 24, and then it said divide by 6.02, but because it doesn't understand scientific notation, it took this answer here and multiplied it by 10 to the 23. And this is what your calculator understood. So in order to fix that, you would have to put this in parentheses, divided by this in parentheses.
Okay.
And then that would fix the issue. Or you could just use that function button where it does this, and then you can just put it in the numerator and the denominator, and then those issues will be fixed with this specific calculator.
Okay.
Okay. Did we recalculate it still 4.15, or did it come out to 4.219 something?
No, I just realized what I did wrong.
You did, okay, good. All right. So here. So you are using the scientific notation button. Oh, and then we hit times instead of divide. That's the only thing. So we'll change this into a divide sign, because if we're doing, it's in the, see that's 2.54 divided, because it's in the denominator. So if we just change this to a divide symbol, then we get our answer. Yes. All right. Okay, back on track then. Okay, so I think most everybody here is using their scientific notation buttons, which is really good. And we can now calculate using Avogadro's number. All right, so this is one molecule of something we call ethanol. You don't have to know it's ethanol, I'm just throwing it out there. We'll hear ethanol later on when we get to organic chemistry and understand that, but for now, I don't want to keep saying C2H6, I'm just going to point out that this is ethanol. So one molecule of ethanol contains 6 hydrogen atoms. And those are the ones in white here, right? So we have one here, 1, 2, 3, 4. There's one back here, 5, and then we have one up here, 6. Right? So it contains 6 atoms of hydrogen. The dark gray ones are carbon, and the red one represents oxygen. Right? So in one molecule, of ethanol now contains, we can actually turn that sentence, one ethanol molecule contains 6 hydrogen atoms, one molecule of ethanol, instead of writing the words contains, I could just say equals 1 I'm sorry, 6 hydrogen atoms. So one molecule of ethanol contains, so it's not saying that this is equal to 6 hydrogen atoms. I know it's not equal to it, but we're just going to kind of refer to this as maybe contains, right? Is that one molecule of this contains 6 hydrogen atoms. So I could write another definition. We could say that one molecule of ethanol contains how many carbon atoms? 2. So we could put 2 carbon atoms. We could say that one molecule of ethanol contains how many oxygen atoms? 1 oxygen atom. One oxygen atom. I think I'm going to rewrite this. I think it might be understood if I just rearrange this here. Let me rewrite this to better understand this concept. I'm going to put atoms, 6 atoms of hydrogen, and I'm just rearranging these words here just to better understand this concept, because it kind of looked like 10 here of oxygen. All right, so one molecule contains 6 atoms of hydrogen, one molecule contains 2 atoms of carbon, one molecule contains 1 atom of oxygen. All right, now, what if I change the number of molecules? What if we change this, instead of 1 molecule, what if I put 2 molecules of ethanol? If I put 2 molecules of ethanol, and I have 2 of these, well, now how many atoms do I have? How many? Yeah, and that would be, how many are here now?
2.
And if I have
Or that'd be 1 now.
1, and then I would have 2. Okay, perfect. So that means I would have 2 atoms. All right. Let's change it. Let's go higher. Let's say I had. If I have 5 molecules of ethanol, how many atoms of oxygen do I have now? 5. So we just simply change this. We can update this. And we say, okay, well, we have 5. Where's my erasers? There it is. Carry on that rag. Oh. This one's a little bit different, but we can get the math because we understand a little bit of what's going on now. Let's say I have 3 molecules of ethanol. Now we're looking at carbon. If I have 3 of these, how many atoms of carbon do I have now? 6. Right? If I have 4 molecules of ethanol, how much hydrogen atoms do I have now? 24 atoms, right? If I have 6.02 times 10 to the 23 molecules, if I have 6.02 times 10 to the 23 molecules of ethanol, well, how many atoms do I have of that? Yeah, I have 6.02 times 10 to the 23 atoms of oxygen. Right? I don't want to go any further than that, but I want to make a connection here with the next concept that we're learning. So if I have 6.02, so if I had 10 of these, I got 10 atoms, right? Because there's only 1 in each one. If I had 100, I would have 100 atoms. If I have 6.02 times 10 to 23 of them, makes sense that I have 6.02 times 10 to the 23 atoms of oxygen. But let's make this simpler, because what does 6.02 times 10 to the 23 represent? A mole. So we could make this even simpler, and we can say that 1 mole of ethanol contains how many moles of atoms, or oxygen? 1 mole of oxygen, which makes this much simpler now, because we're always dealing with huge amounts of atoms here, molecules, that it's simpler. This kind of just simplifies it. So 1 mole of this, I have 1 mole of oxygen. And we can change these up here now. So if I were to say, if I have 3 moles of ethanol, I don't want to know how many atoms I have. How many moles of carbon do I have? 6. I have 6 moles of carbon. If I have 4, well, here, if I have 6, how about this? If I have 6 moles of ethanol, how many moles of hydrogen do I have? 36. I have 36 moles of hydrogen. So we're starting to make these connections now. And this is a lot simpler to understand. The 6.10 times 23 times 5 or times 8 and have these huge numbers that we can just simply think about looking at these in terms of moles. Instead of looking at them as molecules, looking at them as atoms, is that we're now going to look at these specifically as moles. And we understand that in 1 mole there's 6.02 times 10 to the 23 molecules of that. But it's much easier just to say that we have an X amount of number of moles of some element, right? Of some molecule, of some compound. And because we have these equal signs, these are definitions. Is that we could say, somebody, who can I pick on? I need to remember. Anna. Anna. Turn this into a conversion factor. If I put this into a fraction, how would I write this one down here? And what would I put in the denominator? C2H2O, right? And this is a definition. We can also flip this around. I can put 1 mole of ethanol over 1 mole of oxygen. And we can do this for any one of these, right? We can say 3 moles of ethanol for every 6 moles of carbon. Or I can flip that around, right? So let's calculate the number of moles in 48.5 grams of sucrose. And before we move on to this, yeah, I'm not going to need any of this. We're going to learn another new unit. Right? So the one unit we've learned today is the mole. The next unit that we're going to learn, so we have formula mass is in something we call AMU, atomic mass units. Molar mass is in terms of something that we call grams per mole. And we just understood what a mole is, right? 1 mole is equal to, right? 1 mole is equal to 6.02 times 10 to the 23 things, right? That's 1 mole. So now we're going to understand these, what we call grams per mole. Now, on the periodic table, hydrogen is equal to 1.01 atomic mass unit. This comes from the periodic table. We'll read the periodic table. What's the AMU? It's 1.01. We need to convert AMU, into grams per mole. And this is my shorthand here, right? This is the symbol for grams, and I will 99% of the time I'm going to lop off that E and just put MOL. It's just habit after these years. But this represents the same thing. Try and stay away from this. If you do this, you're going to run into issues with calculations. So please, they mean the same thing. Means this, it does. But this is going to cause you headache and trouble. Okay? So try and stay away from that when you're writing out these problems. But we need to learn how to convert now. So this is a conversion. 1.01 AMU, and we're going to convert this into grams per mole, right? So 1.01, we have 1 proton, no neutrons, 1 electron, and the mass of the proton divided by square root, cube root of the electron is going to equal, carry the 1, I don't have my calculator, 1.01 grams per mole. Did we get that? I'm just throwing out a lot of made up numbers. Doesn't mean anything, right? Very simple conversion, right? It's just a 1-to-1 conversion. If I have 1.01 AMU, I have 1.01 grams per mole. Right? On the periodic table, so we have carbon. Another example, carbon is 12.01 atomic mass units. If I want to convert that into grams per mole, it's 12.01. I'm going to put it like this, but again, I don't like the way this looks. It's not how I'm going to use it. I'm going to use it like this, 12.01 grams of carbon for every mole of carbon. This is how I want you all to write it. With, right? It's not per mole of orange juice, right? It's not 12.01 grams of Snicker bars, right? It's 12.01 grams of carbon for every mole of carbon. And if you write it this way, your calculations will be better understood, because we are going to be making calculations where we have to convert grams and moles. Okay? So if we write it like this, try and, even though it means the same thing, just try and avoid that. Okay? It's not wrong, but it's going to may cause you issues when we're calculating. All right? So 12.01 grams per mole. So formula mass, molar mass. Okay? So we're going to start dealing with molar mass now. So anytime we get anything from the periodic table, we're going to think of it in terms of grams per mole. And just to kind of drive this home a little bit more, grams per mole. And we understand mole to be 6.02 times 10 to the 23 things. So 6.02 times 10 to the 23 atoms of hydrogen is equal to 1 mole of hydrogen. And that's what this really represents, this grams per mole. It means that it's going to take this many atoms of hydrogen, to weigh out 1.01 grams. So if we get 1 mole, 6.02 times 10 to the 23 atoms, if I were to put that on a scale, it would calculate out to be 1.01 grams. Right? So that's how we can understand that. Iron, if we remember, iron was 55.85 grams per mole. if we weighed out 55.85 on the scale, and that's how many grams we would have 1 mole of iron. Which means in that 55.8 grams on the scale, how many atoms do we have? We have 6.02 times 10 to the 23 single iron atoms all clumped up together that weigh out to 55.85 grams. So just kind of the relationship that we're seeing there. So now we can get to this problem here. All right, calculate the number of moles in 45.8 grams of sucrose. So what should be the first piece of information that I'm going to write? Yes, so we're going to write 45.8 grams of sucrose. And what is the unit that we're looking for? We're looking for moles, right? We're looking for the number of moles, which means moles has to be where in our problem? The numerator. So we need to get this into the numerator. All right. Grams, moles. Where could we possibly find information that will let us convert grams into moles? Yeah, the periodic table. That's where we would find that information. Right? So earlier, go back into your notes, and we calculated this AMU. What is the AMU for sucrose?
342.34.
AMU of, oops, let me put that a little bit lower. What's the molar mass in grams per mole of this? Yeah, it's the same thing. This is equal to 342.34 grams. And this, again, I know it takes an extra 5 seconds to write this, but it will make your lives much easier. So this is our molar mass, right, in terms of grams per mole. And this isn't the only way I can write it. I can also write this the other way. We can put it as moles of C12, H22, 11 over 342.34 grams. We can also write it like this, right? So we have two options now. If I want the number of moles of this, we have two options, but only one of them is correct. Should we use the top one or the bottom one in order to calculate that? Let's use this one over here. So we can use this and we can say for every mole of sucrose, we're going to have 342.34 grams of sucrose. And that means that this unit here cancels out this over here. And now whatever our answer is here is going to be moles of sucrose. So, somebody calculate this here. Zuri, where's Zuri? You have a calculator? What's our answer here, Zuri?
0.134
0.134 what?
moles of sucrose.
Moles of sucrose. Yes, thank you for that. So 0.134 moles of sucrose. All right, so we can now calculate those types of problems, right? I don't think we're going to jump into this yet. I do want to do a couple more problems here. Let's calculate the number of grams. Yeah, let's do this one here. All right, so here it's asking us to calculate the number of grams. Give us the number of moles, and that's what we're going to start with. We're going to start with 0.125 moles of sucrose. And this time it's asking us to calculate the number of grams. But since I know that there's moles, grams here, I know I'm going to need the periodic table. We've already calculated what this value is, and I have it here up on the board. And for this particular problem, which one should we use, the one on the right or the one on the left? The one on the left, because we want to calculate grams. We're wanting to calculate grams, so we're going to put 342.34 grams of sucrose for every mole of sucrose. And this unit will cancel out this unit, and we can get our answer. Hannah, what's our answer? Believe in you, you got this. You said 7? 7.9, and let's round it to 3 significant figures, so we're going to say 42.8 grams of sucrose. That's a lot of sucrose, but maybe that's what we see in Pepsi 1 or something. I don't know. That seems like a lot of sucrose, but no, I like the calculation. We have our answers. So we've now learned how to convert grams to moles, moles to grams. Later today, we're going to need to add this concept into a chemical reaction. Okay, so let's not forget what we've learned just now, right? Is that we're calculating, we've been able to calculate moles to grams, grams to moles, right? Moles to grams, grams to moles. So anytime that we're presented with something, if we're asked to calculate the number of grams, what is it that you're going to need? Periodic table, right? If you're asked to calculate the number of moles, what are you going to need? The periodic table, right? So if you're asked to calculate the number of molecules, we need Avogadro's number for molecules, for atoms, for particles. But for grams and moles, we simply just use the periodic table to get those values. And we can calculate back and forth between the number of moles and grams there. So here, let's take care of this before we move on to reactions. All right, so here is a chemical equation, right? There's kind of an anatomy to chemical equations, right? This is our reaction arrow, and this is only one type of reaction arrow. We have different types of reaction arrows that we can see. So here, we have this one. We also see them this way. Half arrow, half arrow. This represents a reversible reaction. This is not reversible, right? So irreversible, reversible reactions depending on the reaction we see. So here, this reaction is not reversible. It's going to go in one direction and that's it, okay? Anything on the left-hand side of that reaction arrow we call reactants. These are the compounds, molecules, substances that we're going to react in order to make something. So this is our reactant, this is our reactant, and here on the right-hand side is the product. Okay? Now, we're also going to see these symbols here. S means that it's solid, so the product here is a solid product. Right? We used a solid product, we added carbon dioxide gas, and we got some magnesium carbonate from that. Right? So magnesium oxide plus some carbon dioxide gas, and we get solid magnesium carbonate as our product. And then we see this one down here, this AQ here. AQ is an aqueous solution. Right? When you hear the term aqueous, is there any substance that comes to mind? Aqueous, water, right? Aqueous, aqua, water. So, aqueous solutions are anything that's been dissolved by water. Okay? If I put something into water and it dissolves, that solution is aqueous. Right? That is an aqueous solution if we can dissolve that into water. Now, here we have some phosphorus trichloride, we have some hydrofluoric acid, and then we get phosphorus trifluoride and some hydrochloric acid. Now, this next concept stems from thermodynamics. We can't make energy. We can convert energy, right? Energy can transfer, energy can convert. We can convert energy, but we can't make energy. So, right, law of conservation of mass says that we can't just instantaneously create mass, right? I can't hold my empty hand and instantaneously get a bar of gold and just make gold. I can't make mass. And again, if I was holding a bar of gold, I can't just snap my fingers and have it instantaneously disappear, right? So we can't create, destroy energy. We can't create, destroy mass, right? It has to go somewhere, right? We can transform it, convert it, but it has to go somewhere. So if we notice here, on the reactant side, how many moles of chloride do I have? 3. And how many moles of chloride are in the product? So it means 2 of them just kind of vanished and disappeared. And here, how many moles of, we have 1 mole of fluoride, but on the product side, we instantaneously, we just created out of thin air 3 moles, or 2 moles of additional fluoride, right? So we've kind of broken that law there. So we have to be able to correct it. This is what we call balancing equations. So balancing equations, it's kind of a balancing act that we perform. So if I want to balance this, there's just kind of steps in order to balance an equation. The first thing I'm going to do is I'm going to divide this reaction in half. I'm going to look at the reactant side, and I'm going to do some bookkeeping on the elements that I have. So I know I have phosphorus, I have chloride, I have hydrogen, and I have fluoride. Okay. Fluorine and chlorine. Now, in the exact same order, but on this side of the reaction arrow, I'm going to write the exact same thing. I'm going to write phosphorus, we have chlorine, we have hydrogen, and we have fluorine here. Now I'm going to keep track of some amounts that I have here. How many moles of phosphorus do we have? 1. How many moles of chlorine?
2.
How many moles of hydrogen? And fluorine? 1. And now I'm going to do the same thing with this side. Phosphorus, so I have 1. Chlorine, I have 1. Hydrogen, I have 1. But on this side, fluorine, I have 3. Now our goal here is to make this side equal to this side. So back when we were looking at these definitions here, right? If we're looking at this, this is 1 mole of fluoride is equal to 3 moles of water, but we know that that's not the case. What number could I multiply this by so that it would equal this? 3. If I multiply this by 3, then we can say 3 moles of fluoride is going to equal 3 moles of fluoride. So we're going to take that concept and more shortcuts. This is more shorthand. Instead of actually writing 3 moles, I'm just going to do this. I'm going to put a 3 in front of here because this means that I have not 1, not 2, but I have 3 of them. I have 3 moles of this. So now that I have 3 moles of this, I'm going to update this side here, and I'm going to change that into a 3. But when I did this, I didn't just affect fluorine. What other element does this affect? Hydrogen. How much hydrogen do we have now? 3. So 1 phosphorus, 3 chlorine, 3 hydrogens, 3 fluorine. So we have to, now we're going to work on this side. What number could I put here? Because I only have 1 hydrogen here, but I have 3 here. So if I put a 3 in front of this, I'm going to update that. I have 3 here. And how much chlorine do I have now? I also have 3 chlorine. And now we're going to go back and we're going to say, okay, phosphorus, 1, 1, chlorine, 1, 1, hydrogen, 3, 3, fluorine, 3, 3. So we didn't lose any mass. We didn't gain any mass. So this is good, right? So we've now balanced this equation. So we're going to balance a few more using the same concept, the same process as we did. And putting those values in front. And those values in front are what we call coefficients. So here I'm going to put so the first thing, we're just going to make our list on each side of the reaction arrow. So I have nitrogen over here, I have oxygen, and I have hydrogen. I'm not going to put nitrogen. I want all of the nitrogen listed here. So here we're going to put nitrogen in the same exact order: nitrogen, oxygen, hydrogen. Now let's be careful here because I don't want to know how much nitrogen I have here. I want to know how much nitrogen I have here. So how much nitrogen do I have there? 4. Oxygen, how many?
4.
And hydrogen, how many? 4. And on the product side, how much nitrogen?
2.
Oxygen and hydrogen? 2. Now normally I don't skip around. The first one I just kind of skipped around, but normally I just start from the top and then I work my way down. And I'm taking, so nitrogen here, 4, nitrogen here, 2. Now, one thing to note, this is our subscript, and I'm going to write a note for everybody. Don't change that. Leave this as it is. What we need is we need to put in a coefficient. That's how we're going to fix this, right? We don't change this. We just put in a coefficient that would fix it. So what number could I put here that would make it so I have 4 on this side? 2. So if I put a 2 here, I'm going to cross this out and I'm going to update that and say, okay, well now my nitrogens, they match. But my oxygens don't. So what number could I put here so that my oxygens would match? Rhymes with or. 4, yeah. If I put 4 here, that gives me 4 oxygen. Does that affect anything else? Hydrogen. So how much hydrogen do I have now? 8. So don't forget that we also have to update that because it affects that as well. Nitrogen looks good. Oxygen looks good. Hydrogen needs to be adjusted here. So in order to, and I'm not going to worry about that side. I'm just worried about this side. Okay? So one side at a time. What number could I put in front so that I get 8 hydrogens? So if I put a 2 here, I now have 8. Does that affect anything else? And what should I change that to? To 6. As I have these 2 plus these 4, and that is now 6. That means that this doesn't work anymore. And you will find out that this happens. When you're balancing equations, use pencil. Okay? I don't suggest using pen because sometimes these numbers don't work and we have to go back and change them. So what should this be? Because 2 doesn't work. 3. If I put 3 here, I get 6. 6 nitrogens, 4 oxygens, 8 hydrogens. Okay? But those subscripts do not change those subscripts. All right? The subscripts remain the same. I'm going to give you guys a moment to kind of work on this. There's only 2 elements here, right? So. This one's difficult on purpose. I shouldn't do that to you, but yeah, this one's difficult on purpose. Sometimes this back and forth method doesn't work out very well. So there is another method. When I can't balance an equation, I go to this other method. I give myself one try. If I can't get it in one shot, I go to the second method because the second method, though it requires a little more math, it will give me what I need without any guesswork. Okay, so it's kind of what we call system of equations. It's used in algebra. It is an algebraic technique in order to solve this. So we're just going to make some equations here. I'm going to put the letter A here. I'm going to put the letter B right here, and then I'm going to put the letter C right here. I forgot this plus sign. That might have thrown everybody off. But here, I'm going to put C. Now, I'm going to make equations for this. There's going to be an equation for phosphorus, and there's going to be an equation for hydrogen. Now, I'll walk you through this one, and then the next one I'm going to kind of ask for some answers, but this is what I would write to make my equation. Since I have 2 phosphorus, I'm going to put 2A. Because it's 2 times whatever the number is in front. We just don't know what that number is. Plus 4A. I'm going to treat this as if it was an equal sign, is equal, nope, back up, nope, that goes down below. We're only doing phosphorus. Sorry, let's backtrack. We're just concentrating on phosphorus. Phosphorus is 2A, equal sign, and I'm going to go find my phosphorus here. So how many phosphorus do we have here?
1.
So I need to put 1B plus, what would I put here? 4C. So this is my one equation here, right? We're looking at just phosphorus. We're going to ignore hydrogen for a second. So we have 2A equals 1B plus 4C. Now we'll do hydrogen. What would I write for hydrogen? 4A is equal to 3B. And that's for hydrogen. Now we're just going to write these. I want to know what A is, I want to know what B is, and I want to know what C is. We are going to now start putting numbers in. And I could use 1,006,585 for A, but I don't need a ridiculously high number. Okay? What is a simple number that you can make A and figure out what B is?
3.
What is it?
3.
3. Perfect. If I force and choose A to be 3, then what is B?
4.
4. So now I have two of the answers now. One is 3, one is 4, and I just need to figure out what C is. And I can use this equation because I know what A is. We said that A, Adam said A, make that 3, and we're going to make B 4. So that means that 6, I'm going to continue this down here, 6 is equal to 4 plus 4C. Minus 4 on this side, minus 4 on this side, and we're going to get 2 is equal to 4C. And that means that C is equal to don't be scared of fractions, 2 over 4. Does everybody see how it's 2 over 4? All right, this is just math. Can someone simplify this for me real quick? What is it? In a fraction. 1/2, right? So C is equal to 1/2. And this is where students panic. They go, oh no, it's a fraction. Alice, what do you mean? I want to get rid of this fraction. If I multiply this by 2, I have to multiply this by 2, and I have to multiply this by 2. 6, 8, and 1. A is 6. B is 8. And C is 1. And there's no guessing game there. Do you have to use this method? No. Could you keep going back and forth and trying to figure this out? Absolutely you can. 100% you can do that, but again, this is just a different method. Let's try this back and forth method. It does get a little messy, but you are able to use it. Out of frustration, I just give myself one attempt. If I can't figure it out in one attempt, I start using that second method. But again, it's not mandatory. So here, we're going to put P and H, and over here, we're going to put P and H. I have 2 of these. I have 4 of these. I have 5 of these and 3 of these. Well, there's absolutely no number I can multiply this by that's going to give me 5 hydrogens. We're not going to multiply by decimals or fractions. Is that here, I now need a number that both 2 and 5 go into. What number do 2 and 5 go into? 10. So I need 10 on this side and 10 on this side. So I'm going to put a 5 over here, and that's going to give me 10 here. And how much hydrogen does that give you? 20. And I'm probably going to have to scoot this over. This is going to take a few attempts here. I'm just going to scoot this over. Here, now we kind of have to decide, make a decision here, is that I need to get 10, which means I have 4, I have 5. I could put a number here and then add 4 to it, right? Or I could put a number here and here, you know, but I don't want to make things too complicated. So if I put if I put a 6 here, I got these 6 plus these 4, and that's going to give me 10. And hydrogen, that gives me 18. Well, phosphorus looks good, but unfortunately hydrogen doesn't. I need more hydrogen over here, which means 6 isn't going to work for me. If I do 7, 7 times 3 is 21. I'm a bit over by 1. And this is where we have to do some thinking, because I need this in multiples of 4. Right? So 7 really isn't going to work for me. So let's try 8. This is going to give me, if I do 8, over here I'm going to get 24. But phosphorus, I do have to, there's 8 phosphorus, there's 4 phosphorus, this is now going to be 12. Well, so instead of 5 here, I'm going to increase this by 1, turn this into a 6. I get 12 phosphorus, and I get 24 hydrogen. So the back and forth method still works, right? Just takes a little more time. Or you can use the system of equations. You know, the general chemistry students use that. It's great. Almost time for a break. Let's see. We're going to go sodium. And we're just going to use the back and forth method here. We're going to have sodium, hydrogen, phosphorus, and oxygen. Sodium, yep, there we have. Over here, sodium, phosphorus. Let me do hydrogen first. Let me put it in the exact same order. Hydrogen, phosphorus, oxygen. How much sodium do we have? We have 1 sodium. Hydrogen, how much hydrogen do I have on the reactant side?
3.
3. How much phosphorus? 1. How much oxygen do I have? 5, yes. Everybody see there's 4 here, there's 1 here, and we add them both up.
Why didn't you have 2 sodium?
Oh, you're absolutely right. You're absolutely correct. This would be 2 sodiums. So 3 sodiums here. We have hydrogen, 2, phosphorus 1, oxygen 5. So again, another issue where we have some odd values here. 2, 2, 3, yep, all right. So we're going to have to find least common multiple again. What number can sodium, right? 2 and 3 can both go into what number? 6. Now, we have a choice here. Let's start with this side. I'm going to put a 2 over here. And that's going to give you 6 sodiums, but this also affects what? How much phosphorus do I have now? And how much oxygen do I have? 9, right? These 2 times 4 is 8 plus 1, and I now have 9 oxygen. Since we have 2 phosphorus over here, I need a 3, right? I need a 3, but this one's not pretty. If we put 3 here, I now have 6, 7 hydrogen. In phosphorus, I have 3 hydrogen. And oxygen is 12, 13. Ah. Oh. It starts getting a little messy. Okay? We could keep going, okay? But I'm going to have us backtrack because there are other options that we have in order to try and solve these. So we need to look at a larger picture. So we are going to see if there's another option that would help us out. And we have 2 here, 3 here, 1 here, 5 here, 3, 2, 1, 5. Now, yeah, I know I need to get more over here, right? There's no number I can multiply by 2, but notice that sodium is in 2 separate ionic compounds here. So we could put a 2 here, or we could put a 2 here. And that would also just give me 3. Right? Because phosphorus is already even, maybe it would make sense not to touch phosphorus for now. Maybe we can just put a 2 here. If I put a 2 here, well, that definitely gives me 3. My hydrogen is these 2 plus these 2. Now I have 4. Phosphorus is left alone. Oxygen is now 6. And we'll say 3, 2, 1, 5. So we don't need to touch sodium here on the product side. We don't need to touch hydrogen. We don't need to touch, oh, we do need to touch hydrogen. So what number could I put in front of hydrogen here so that I get 4?
2.
2. So 4 here, and that also gives me 2 more oxygen. So I get these 4 plus these 2, and now it's 6. Right? So if they get a little messy and you're not getting it, 2 options: start over, try a different direction, or use those system of equations and figure it out that way, right? Both methods work. And I think one last topic before I cut you loose for a break here. Let's go with calcium phosphate. Now, when we're determining the number of elements, because this may come up when you balance equations, I'm going to put the same formula up here, but I'm going to make a change to it. So there's calcium, phosphorus, oxygen. So how much calcium do we have here? 3. How much phosphorus? Right, because remember this goes here, this we multiply across, right? So there's 2 here, and oxygen, 8. If I put a coefficient in front of here, let's put 3. This applies to this and applies to this, right? But this applies to this, applies to this, and applies to this. Means I have 3 of these. So we need to multiply across when we do that. So if we list calcium, phosphorus, and oxygen again, how much calcium do I have?
9.
9. How much oxygen do I have? So 3 times 1 times 2?
That's
6. 3 times 4 times 2? And that's how we would take care of that there, right? So 3 times 4 is 12, 12 times 2, 24. So we can account for all of the moles of all of the elements that we have here, right? So it may come across in some other balancing situations, especially for today's lab. That topic will come up. So let's take a break for at least 15 minutes. Let's go, let's come back at 10. Come back at 10. We'll continue. All right. All right, so we're going to go over some different reactions. So the way we see different compounds will kind of tell us, it'll give us some insight as to the product that we're going to make, right? Just by looking at the reactants that we have. So in these examples here, these are all what we call combination reactions. And just as the term refers to, is that we're going to take these reactants and combine them together. Right? So we're only going to get one product in these reactions. And then we see just kind of a general formula. This isn't written in stone, but it is just a general formula. Is that we have A, right? Compound A plus compound B, and we're going to get compound AB, right? So we can consider this to be a combination reaction. We could also do this, A plus B plus C, and we're going to get A, B, C, right? This would also represent a combination reaction, is that we have multiple reactants and we combine them all together to get one product, and we see that as a combination reaction. So, right, so 2 moles magnesium plus some oxygen, we're going to get magnesium oxide, that's one product, right? Here we have 2 reactants, we're going to put them all together, and we're going to get some sulfuric acid. So again, combination reaction. Then the next one is just the opposite of that, a decomposition reaction, where we're going to take one reactant and break it down into multiple parts. So here we see aluminum nitride, so 2 moles of aluminum nitride, and we're going to it's going to go in a decomposition reaction and get 2 moles of aluminum and 1 mole of nitrogen gas. The next one, we're going to break that down. Right? We have calcium carbonate. It's going to break down to calcium oxide plus some carbon dioxide gas. So we can see that those are what we consider decomposition reactions. So the general formula, right? Again, not written in stone. AB, we're going to get A plus B. Similar, we have one reactant. We're going to break it down into multiple parts. And maybe even this. What if we did, A plus, right? Still decomposition reaction. We have one reactant. We're going to break it down into two or more products. So decomposition reaction. The fourth one is known as a single replacement reaction. Single replacement. One of the elements in the reactant is going to get replaced. So our general formula for that, A plus BC, single replacement, one of the elements is going to get replaced, is that this element here, B, is going to get replaced with element A. And we're going to get B plus AC, right? Single replacement reaction. Let's take some hydrogen gas. No, let's take some, what do we use here? Hydrochloric acid. Yeah, let's use that. So let's use zinc solid plus some hydrochloric acid, that's aqueous, single replacement reaction. Right? We're going to replace the zinc for the hydrogen, right? Hydrogen's going to get replaced. And actually I should put 2 here. That we're going to get zinc chloride plus we're going to get some hydrogen gas. Okay? And make a note of this one. This is going to be in your lab today. So make a note of that one there. But here, right? So single replacement reaction. Right? That's what we see over here. The lead is going to be replaced with the chromium, and then we get chromium nitrate plus lead. The copper is going to get replaced with the iron, and we get iron sulfate in copper, right? So we have one of these elements being replaced, giving us some single replacement reaction. And then if we could do a single replacement, we can also do double replacement reactions, where 2 of the elements will be replaced, right? Not just one, but we're going to have 2 elements being replaced. And I'm going to have you, I think your textbooks, I'm going to show you how I think if they didn't correct it, the publisher or the author, I believe your textbooks say this. Your textbooks say this? CB, or does it say BC? Okay, so it does say, okay, it doesn't say CB. So do me a favor and write CB. All right, that'll correct some errors here, and I'll show you why with just this first one here. I'm gonna leave this the way that it was. And let's go with silver nitrate plus some potassium iodide. And we're going to get some silver iodide plus we're going to get some potassium nitrate. Okay, so this is our answer here. And underneath, I'm going to do something underneath here. So as far as AB goes, this is a polyatomic here, right? And we treat them as if it's just one unit. So this is A, the nitrate is B, potassium C, iodide D. So we're going to put A and D together. So double replacement, A and D are going to go together, and B and C are going to go together, right? So we're going to get AD, A is silver, D is the iodide. But your books say to do this, BC. Take B and put it together with C. But this is the correct answer. Right? So this is why I asked you to do CB and not BC. It's always cation, then the anion. Right? Cation, the anion, and here we don't see that. So for this reason here, just kind of change that to CB, but we can see the double replacement reaction occurring here. So double replacement reactions like this are commonly seen in what we call precipitation reactions. Right? Precipitation reactions, acid-base reactions, which we'll get to next week. But precipitation reactions, and you're going to see it today in today's lab. We're going to take some chemicals that are clear, we're going to mix them together, and we're going to form some solid out of those solutions, right? And the solids, we know those as precipitates, right? So the precipitate is going to be our solid. So here, if we put silver nitrate and some sodium chloride together, we're going to get silver chloride, this white precipitate, plus some sodium nitrate, right? Now, the solid, they have a term for the solid, what we call it insoluble. Right? If something dissolves in an aqueous solution, or something dissolves in water, we consider that to be soluble, right? It dissolved, that's a soluble solution. But when something forms a solid, that solid is something that we consider to be insoluble, meaning it's not soluble. Right? So this is a solid, it's not soluble, it's not going to dissolve in water. In your textbooks, you have this table. You'll also have it in the lab, which you'll need for today. But I just wanted some to show you, just to give you some clarity on this. When we're looking at solutions. So in this particular case here, let me erase this bottom one here. When we're writing these reactions, we have to determine which substances are going to be aqueous, which ones are going to be gas, which ones are going to be solid. And this table kind of helps us determine between the soluble and insoluble products, right? Is that here, even for the reactants, silver nitrate. Well, we need to know if it's aqueous or if it's solid. So always look at the anion. Pay attention to the anion, nitrate, pay attention to the iodide. And we can see here that soluble compounds, nitrates. And if you haven't memorized your polyatomic ions yet, the table doesn't do any good for you. Right? You're just not going to understand it, unfortunately. So here it says nitrates. And I've memorized mine, and I know that this is nitrate. And nitrates here are soluble. If something is soluble, understand that is aqueous. Aqueous, aqueous, potato, doesn't matter. But nitrates are all soluble compounds, meaning nitrates are all aqueous solutions. And then it says exceptions, right? There are exceptions to the rule, just like our periodic table of elements, right? Nickel, silver, zinc, those are exceptions to the rule. They don't need any Roman numerals. These are exceptions to the rule for it. Now, nitrates, look at it this way. Are there any exceptions to the rule as far as nitrates are concerned? Because these exceptions here, lead, 2, silver, and mercury, are exceptions for chlorides, bromides, and iodides. Right? So these are not exceptions to the rule for all of these. All right. So as far as nitrates are concerned, is there any exception to that rule? No. Nitrates are always, doesn't matter what it's with, nitrates are always going to be aqueous. So is this aqueous or is this solid? Aqueous, because it's nitrate. So we can designate this as being aqueous. Now let's look at potassium iodide. Well, iodides are soluble unless it's with lead, silver, or mercury. If it's with lead, silver, or mercury, they're going to be solid because those are the exceptions to the rule. But as far as potassium iodide, is potassium one of the exceptions? No. So potassium iodide would also then be soluble. It's aqueous. This is silver iodide. Is silver an exception to the rule? Yeah. So if silver's an exception to the rule, well, that means that that's going to be a precipitate, and that's going to be solid. So we have some other practice ones here to look at, right? And again, you really need to know your polyatomic ions, because here I need to know what is the name of this polyatomic ion. Sulfates, right? This is sulfate. So now if I go down the list, I'm just looking for sulfates. Okay, here's my sulfates. I understand sulfates to be soluble or aqueous unless it happens to be with calcium, barium, or lead. Is potassium one of the exceptions? No. So is potassium sulfate aqueous or solid? Aqueous. Magnesium nitrate. Well, here's my nitrates. Any exception to that rule? Is this aqueous or solid? Aqueous. Lead, what is this here? Acetate. So I'm going to go down this list. Acetate. Well, acetate also doesn't have any exceptions to the rules. Is this aqueous or solid? Aqueous. Calcium sulfate. Go back to my sulfates. Oh, calcium is one of the exceptions, and calcium is going to be solid. Silver, what is this here?
Phosphate.
Phosphate. So we go down to the phosphates. Now it kind of changes there. The table changes. These are insoluble, meaning that phosphates are solid. But they'll be aqueous with these exceptions here. So we go to phosphate, silver, phosphate. Is silver one of the exceptions? No. Which means it's going to remain insoluble, so silver phosphate is a solid. Barium hydroxide. Here's hydroxide. Oh, barium hydroxide meets one of the exceptions, and it's not going to have a precipitate, so it's going to be aqueous, right? Because it's not going to have a precipitate, it's going to be aqueous. And then silver chloride here. Here's chloride, silver's the exception, and it's going to be a solid. So this table kind of helps you determine which one is going to be which. Now, for double replacement reactions, you are responsible for knowing. You're responsible for knowing how to write a reaction. Right? How do I write a combination reaction, a decomposition reaction, a single replacement reaction? The most difficult one being our double replacement reactions. So precipitation reactions, acid-base reactions that we'll get to next week, is that we need to know how to write these reactions if you're only provided with the reactants. You have to determine what those products are going to be. So we're going to spend some time on that. And there are steps. This is kind of a lengthy process. There are multiple steps in order to write a reaction. I won't keep this on the board yet. I do have some slides to get through, and then we'll do some examples. So here, this is the model we're going to use, right? AB plus CD And I'm going to write these steps down here because we're definitely going to need them. So step 1 is that we're going to take reactant AB plus reactant CD, and we're going to make product AD and product CD. So I've kind of identified these here for us, is that the magnesium is going to be A, the chloride is going to be B, the sodium is C, and the hydroxide is D. When we put A and D together, we get magnesium hydroxide. When we get C and B together, sodium chloride. And students kind of say, well, Alex, why did you write this, but you didn't write this? Because clearly there's 2 on the other side, and if I do this, I only have 1. Writing these reactions takes multiple steps, and we don't want to mash all the steps into just one. Right? I know that there's going to be more chloride on one side than the other, but that's a different step, and we're only on step 1. Step 1 says this. Step 1 doesn't say to do this. That's not what step 1 says. Step 1 says, take whatever C is, take whatever B is, and put them together. So that's what's done over here. Now, polyatomics, we treat them as if they're one unit, and we don't carry over the number of moles, right? We don't carry over the number of moles there. All we want to do, put whatever A is and D is, put them together, take whatever C is and B is, and put them together. We'll balance in a different step, okay? But one step at a time, okay? The next step is we need to make the products neutral. I already know the reactants are neutral. I don't have to worry about this. I know that magnesium chloride and sodium hydroxide, as they're written, they're neutral solutions. So step 2 are products neutral, right? We know about charges. We all know how to put these elements together to make compounds. And when we look at this, when we look at MgOH, right? Magnesium, what's the charge on magnesium? It's in group 2, by the way. So it's 2 plus. Anybody know the charge on hydroxide? 1 minus. So sitting here, is this neutral? No. We need more hydroxide. So in order to make it neutral, we need 2 of them. And that's what we've done up here. Now, kind of going back to this versus this. Students want to do this, but don't. Right? This is 1 plus, this is 1 minus. The answer is NaCl. Students are tempted to do this, and then they end up doing this. They go, this is 1 plus, this is 2 minus. Oh, I guess that means I need 2 of these. And then they make it even worse, right? They just kind of make the problem more difficult by carrying over those subscripts. Okay, so don't be tempted to do that. We just put A together, we put that together. There is a time when we need to do that, and I'll explain it in some of the lab examples. Okay? But for right now, this is what we're working on. Now, well, we made the products neutral, but we can see that chloride on one side has more than the other side. So the next step, our step 3, would be to balance the equation. So we're going to balance the equation. So for these here, it's already difficult enough to put the reactions together. We don't want to complicate that process. We're just going to take some mental notes. We're just going to do some back and forth. Okay? And we'll end up getting the right answer. So there's no list to make for this. We'll just do a little back and forth. How much magnesium do I have here? And over here I have, how much chloride do I have here? And over here I have, so what number could we put in front of the sodium chloride? 2. And if we put 2 in front of there, well, that means I have 2 sodiums. So over here, I'm just going to put a number 2. And now we have 2 sodiums. But this sodium also affects this hydroxide, which means I have 2 hydroxide. And over here, it matches, we have 2 hydroxide. So it's just a little back and forth. We don't need to make a list for this one. Just a little bit of back and forth. And we now have a balanced formula equation. Balanced formula equation. When we mix these solutions together, this is not how it looks in an aqueous solution. When we dissolve these, they separate into ions. So they separate into ions. So we put this into water and they all separate. So we get, oops, let me separate those. They all kind of scatter. And this is more or less what it looks like in the solution, right? They all separate into ions. And then all of a sudden, some of these ions bump into each other. And we end up with this solid clumped at the bottom. Right? So this is the reaction that took place. We put some magnesium chloride together with some sodium hydroxide. They all dissolved in the solution, but at the very bottom we did create a precipitate of magnesium hydroxide. We have to be able to represent this in a chemical equation. Okay? So we can't just draw pictures for everything, it'd be nice, but we actually have to be able to represent this in some chemical equation. So this is what we call a balanced formula equation. The next thing we're going to do is something we call a complete ionic equation. Is we're going to take all the reactants and we are going to separate them into ions just like this. And that's what we see down below over here. Let's see our minus in there. That looks, yep, that looks good. Oh, my God. All right. So we take our reactants. We're about to put them in the beaker and separate them. So here we see magnesium 2+. It's been dissolved. It's aqueous. It's an ion. So anytime we see an ion, we assume all of our ions are always aqueous, that they've dissolved. And notice that we have this 2 here. When I write this, if I write this, this represents this. But that's not what we have up there. What we have is we have magnesium bonded to this and bonded to this. So the chlorides aren't bonded to each other, right? The subscript 2 means that we have 2 atoms bonded to the magnesium. This is why we write it like this. We don't put a subscript 2 back here. We have 2 moles of these chloride ions. That's what we see in the beaker here. There's 1 mole here, and there's another mole over here. So we have 2 moles of this. So we separate them into ions. I got magnesium ions, 2 chloride ions, Now we're going to separate this. I have 2 moles of sodium ions. There's 1 mole here, there's 1 mole here, and I also have 2 moles of hydroxide. There's 2 moles here, and then there's another mole here, that's 2 moles there. And then our product, well, notice we didn't separate the product. Well, because in our beaker, it's not separated. It's at the bottom of the beaker, magnesium hydroxide, solid. And then we still represent our 2 moles of chloride, 2 moles of sodium here. So that equation there represents what we see in this beaker. We're going to separate everything into ions except for the solid. Everything else is separated. Now, the last part is what we call the net ionic equation. So this is the complete ionic equation. The net ionic equation represents the actual chemistry that made the product. Right. There's a math concept that I want us to think about. If I wrote this, y plus b equals x plus b. Can somebody simplify this for me? Y equals x, right? If I have this over here and I have it on this side over here, they simply just cancel out, right? Because they're identical. So looking at this, if we were to treat this as if it was an equal sign, doesn't this look exactly like this? And this looks exactly like this. Which means they're not actually part of the reaction. That's not what made the hydroxide. Do I have magnesium 2 plus aqueous ions on the other side? No, I don't. I have magnesium there, but I don't have the magnesium ions. So anything that's not needed can simply just be crossed out, right? If this I can cross out, this and this I can cross out, and then everything that I didn't cross out, everything that you don't cross out, this is what we consider the net ionic equation, right? Anything that we didn't cross out is the net ionic equation. I don't want to do this one. Actually, I want to get into the textbook, and let's do some from the textbook. This is Lab 4. We had one earlier where we did zinc and hydrochloric acid, zinc and HCl. That's going to be reaction number 8, right? If I look at Lab 4 on lab page 4-4, the zinc, the hydrochloric acid, it's reaction number 1. So you should be good with that one there. It was a single replacement reaction. But let's jump into some of these other ones here. And we'll do number 2 and we'll do number 5. So we'll do the second well and the 5th well, and that should probably set you up for the lab pretty good. Okay, so we need to make a reaction. I'm going to lift this up here. Mute the display screen. And it says in the second well, I'm on lab 4-2. So not the unit, but the lab in the back of the book. Yeah, so lab page 4-2, and we're looking at the second well, and it says we're going to put in 3 drops of lead 2 nitrate. So lead 2 nitrate. Plus, we're going to add some potassium iodide. All right. So here, step 1, I'm going to add a 4th step here, which product is neutral. So step 1 says that we need to put A and D together and C and B together. So this is going to be A. This is going to be, this is going to be B. This will be C, and this will be D. And before we go on, I want to know if these are aqueous or if these are solid. I could use the table, which is on the next page, or I can just think about what I'm reading here. And it says that I mixed 3 drops of lead nitrate. Is that aqueous or solid? Aqueous, because I put drops of them in. Right? So I know this is going to be aqueous. And if I put in 3 drops of potassium iodide, is this solid or aqueous? Aqueous, right? Because we put in 3 drops. So I don't even need the table for those. So step number 1 says we're going to take A and D and we're going to put them together. So this is A. And this is D. And now we're going to put C and B together. So C is potassium, and then I have nitrate. But I'm going to do a few things here, and we're going to select the right option. Only one of these is correct. Now, it's said to put C and B together. What is C? It is potassium. And what is B? Nitrate. So I need to put potassium nitrate together. Is this potassium nitrate? No. This is potassium nitrate, but if I did this, it would represent CB2. But it's asking us to do just CB. This is C, this is B. So why is it okay to bring this 3 over, but how come it's not okay to bring this 2 over?
Because you have 1 nitrate?
Because, yeah, if I, this is nitrate. If I remove that 3, well, it's no longer nitrate. We already agreed with that it's not nitrate. So I have to bring that 3 over because that's what B is. B is nitrate. But remember this other stuff, I don't need to know, it doesn't matter how many moles of it we have. That's balancing, it's a different part of the process, right? That's step number 3. Okay? So that we don't need. So it is just this one up here. We don't need to bring those other ones over, just this potassium nitrate. So step 1 is done. Are the products neutral? Well, iodine is -1 and potassium is +1. We get those from the periodic table. Group 1, group 7. Does anybody know the charge on nitrate? 1-. Lead is one of our exceptions. Lead needs a Roman numeral, which means it could be +2 or +4, so we don't know. But since we know this and we have 2 of them, what's the charge on lead? 2+. And now I'm just going to transfer those units over here. If it's 2+ over here, it's 2+ over here. This is 1-, 1+, 1-. Is potassium nitrate neutral? Yeah, it's a good compound. We put them together as neutral. Is this neutral? No. How do we fix this? Add it to where? To the iodine, right? So now this is neutral. Okay. So now step 2 is done. Now we're going to balance the equation. We're just going to go back and forth a little bit. Let me erase some of this here. We don't need this anymore. 1 lead, 1 lead. How many nitrates do I have? Don't say 6. 2. There's 2 nitrates here. How many do I have here? Don't say 3. 1, right? This is 1. There's 3 oxygen, but there's only 1 nitrate. So what number can I put in front here? We put a 2 here, but that changes potassium. I have 2 here now, and over here I only have 1, so what do I put in front? That means I have 2 iodide, and over here I have 2 iodide, so we're balanced. Now, which of the products is neutral? Well, we probably should memorize this one since it's so simple, right? Any exceptions to the rule for nitrate? No. Which means this is aqueous. And we can verify this. If we look on the next page, 4-5, we're going to look at iodide. The exception to the rule happens to be lead 2. So this is going to be solid. So this is our balanced formula equation. All right. Next comes, so this is our balanced equation. Next we're going to do the complete ionic equation. This is where we separate everything except for the solid. Anything that's listed as aqueous, right? These are going to be split up into ions. So I'm going to split this one up here. This is now lead. And I need to have this charge here. This is an ion now. Is this ion aqueous? Yes, it's aqueous. Yep, there we go. This is aqueous. And now I'm going to add in, so plus the next one. How many nitrates are in the solution? 2. So we're going to put 2 nitrates that are also aqueous. The plus sign, we're going to break this up here. That there are 2 potassium ions, but there's also 2 iodide ions, so plus 2 iodide ions, both of them being aqueous. The solid, do I need to split the solid up? No, because that's a solid, so we're going to put Pb, I2, solid, aqueous. I need to split this up. There are 2 potassium ions, and there are 2 nitrate ions, and both of them happen to be aqueous. Now we're going to do the net ionic. The net ionic equations, anything that I can cancel out here that we see. It's the same on both sides of the reaction. Yep, the 2 nitrates can go away. Anything else? The 2 potassiums can go away. Anything else? I don't think so. So this now, whatever's left over, Pb2 plus aqueous, plus 2 of these. This is aqueous. And I need to get Pb, I2 solid. And we're going to backtrack for a minute. See how this says this is an ionic equation? I need to have charges here and here. Complete ionic equation. I need to have charges with anything that's aqueous. The balanced chemical formula, let's remove those charges. Right. So the balanced formula, we don't need those charges. For the net ionic equation, make sure everything but the solid has charges. For the net ionic, make sure everything but the solid has charges on it. Okay? We're going to do one more. We'll do it on this half of the board. And then I'll leave this one up for the lab that you guys can all reference. Let's do number 5, I said. So 5 is going to be, let's see, some calcium nitrate. Some calcium nitrate. Plus, we're going to have some sodium phosphate. This represents A, nitrate B, this is C, phosphate is D. So first step, can somebody give me what's the reactant or the product we're going to have first? So calcium phosphate plus the next one is going to be did I do that correctly? No. Right? Do I need this 3 here? No. The 3 goes away because we're not going to bring that over. Do I need this 2 here? No. We can get rid of that one. Do I get rid of this 3 here? No. Yeah, this is what we need here. So we need to keep that one there because this is nitrate. All right, so now step 1 is done. All right, so step 2, are the products neutral? We need to know the charges. This is 1 minus, this is 2 plus. This is, actually, there's no transition elements here. So 2 plus, 3 minus, 1 plus, 1 minus. Is sodium nitrate neutral? Is that good? Yeah. Is this aqueous or solid? It's nitrate. Nitrates are all aqueous. All right. We put in 3 drops of this. This is aqueous. We put in drops of this. This is aqueous. But this is 3 and 2. We need to fix this. So calcium's 2 plus. Phosphate is 3 minus. 2, 3 both go into 6. 2 goes into 6 how many times? 3. 3 goes into 6 how many times? So we need 2 of these. All right. So now the products are both neutral. And let's verify that this is solid. We can go to the next page. We go to phosphates. Phosphates are insoluble. And it's with calcium. And calcium is not one of the exceptions. That this is our solid. All right. So all these steps are done. So let's do the net ionic equation. So we're going to break everything up into ions here. Calcium, aqueous. I have 2 nitrate ions. These are aqueous. I have 3 oh wait, no. Oh, let's back up. I skipped a step. I did skip a step. We didn't balance this, did we? No, we did not. Let's backtrack. Before we do that, 1 calcium here, 3 here. What number should I put here? 3. How much nitrate do I have here? 6, right? These 2 times 3 is 6. So what number do I put in front here? 6. Now that gives me 6 sodium. What number do I put in front here? 2. 6 sodium. How much phosphate do I have now? Rhymes with ooh. 2, right? Yeah. So over here I have 2, right? This is 4 oxygen, but 2 phosphates is what we have here. All right. So now let's continue on with the ionic mixture. I'm going to just change this to 3. And this is going to get changed to 6. So does everybody see that? So 3 calcium ions plus 6 nitrate ions. How many sodium ions do I have? So 6 sodium ions, aqueous. How many phosphate ions do I have here? 2, so plus 2 phosphate ions, also aqueous. Do I split the solid up? No, we're going to keep that together. So 3 PO, 2 solid, 6 sodium ions, aqueous. And how many nitrate ions do I have? 6, right? 6 nitrate ions that are aqueous. So from here, we go to the net ionic. Which ones can I cross out? The nitrate and the sodium. Anything that we don't cross out is our net ionic equation. So we got 3 calcium ions plus 2 phosphate ions. And that's going to give us our solid precipitate in the reaction, right? So, net ionic equation. All right, luckily for us, we're not almost done. All right, plenty more to go. I'll just talk as you guys are kind of writing stuff down here. All right. We'll talk about what we call redox reactions. So redox reactions involve electrons that are being shifted around. We've seen moving electrons around as we're putting elements together, or compounds together, net ionic, or ionic compounds. So redox reactions and non-redox reactions. So a redox reaction involves electrons that are being transferred. Non-redox reactions, well, that means no electrons are being transferred. So those two types of reactions. And when electrons are being shifted around, there's two other terms that we need to understand. One we call oxidation and reduction. Oxidation and reduction. So, right, oxidation is a loss of electrons. Right? Some element is going to lose electrons, and we'll note that is that particular element being oxidized, right? Or substance being oxidized, right? Reduction, it seems kind of counterintuitive to say that reduction is a gaining of electrons. But what's getting reduced is that negative charge. Okay? It's a negative charge that's getting smaller. A negative charge that is getting more positive as it gains electrons. So the negative charge, because we've looked at our ionic compounds, right? We have some metal that has a positive charge and a cation, and then we have our anion that's always the non-metal, right? And it's gaining those electrons. So the negative charge, right, is becoming less negative as we reduction gaining those electrons. So let's take a look at this. Let's just take a look at nitrogen. So nitrogen, atomic number 7. Nitrogen has how many protons? It's atomic number 7. 7. Perfect. And it has how many electrons? 7. All right. Now, here, if nitrogen were to transfer, let's see, it's going to lose electrons, and over here we're going to put gain electrons, right? We gain electrons. I might have misspoke. I hope I didn't misspeak earlier, right? So if it gains electrons, right, it's called a reduction, right? But it's going to get more negatively charged. I think I misspoke and I said more positively. I'll have to check that. But gain electrons, it's going to become more negatively charged. Okay? Lose electrons, it's going to become more positively charged. So let's say that nitrogen was in a redox reaction and it lost or transferred, we'll say 3 electrons. So if it loses 3 electrons, how many electrons does it have left? And the number of protons stay the same. let's say this one gains 3 electrons. We'll say that this one actually is going to gain, yeah, we'll gain 3 electrons. If this gains 3 electrons, how many electrons will it have? 10 electrons. So here, we're going to give this an oxidation number, which is different than a charge. Okay. We're just shifting electrons around. This is not the charge. This is its oxidation number. And the oxidation number here is this is plus 3, and this is minus 3. And here the oxidation number, if it's neutral, the oxidation number is simply 0. So as we lose electrons, right, this is oxidation. As we lose electrons, nitrogen undergoes oxidation and gets a plus 3 oxidation number. Oxidation number. It's not its charge. If I want its charge, I'm going to go to the periodic table. I see it's in group 5, 5 minus 8 minus 3, and the charge is 3 minus. Because that's what I've been showing you. If I want the charge on calcium, I put 2 plus. I've never written it as plus 2. It's been 2 plus. If I want the oxidation number of calcium, I'm giving it this number here, plus 2. That's the oxidation number. So this is not the charge of nitrogen. This is its oxidation number. So this is not the charge of nitrogen. This is its oxidation number. If I want the charge, again, I go to the periodic table and I can get its charge from the periodic table. But this is its oxidation number. So when we say that this is reduced or reduction, this nitrogen was reduced. And maybe in order to keep things, I always in a reaction or in any element, I try and find the one that's reduced first, because it's always the one where the number got smaller, and that's kind of how I relate reduction. I look at the oxidation number. This is 0, and it went to -3. This was obviously reduced because that oxidation number got smaller. So if I have, let's use phosphorus. If phosphorus goes from a +1 to 0, did the oxidation number get smaller? Yeah, 0 is less than 1. So phosphorus was reduced because that number got smaller. If I put phosphorus -1 to phosphorus +1, did this oxidation number get smaller? No, it got bigger. So was this phosphorus reduced? No, it was oxidized. And that's how I always that's just what I use. You can memorize the rules, gain, loss, gain electrons, do all the math. But just to kind of relate it quickly, I just always look at the oxidation number and determine whether it got smaller or bigger. In this case here, it got smaller, this was reduced. In this case here, it got bigger, this wasn't reduced. And if it's not reduced, I have no other choice but to label it as being oxidized. Right? So these rules have to be memorized in order to, and you've got a couple weeks to memorize these rules. Our exam is not next week, it's the following week. So we're going to spend 2 weeks on these units here. But you do have to memorize these rules. I kind of lightened them up a little bit. In your textbook, these rules are on page 4-14. 4-14. But it's kind of, it might be a little bit wordy, I don't know. I just kind of, I separated them into 5. And this is how we determine oxidation numbers. We don't go to the periodic table. I go to the periodic table, I'm looking for charges. If I want to know oxidation numbers, I'm going to use these set of rules in order to determine oxidation numbers. Okay? So, rule number 1. Hydrogen is always going to be +1. Pretty simple. Hydrogen +1, oxygen -2. So if we had, let's see, what can we write for hydrogen? No, let's not use lithium. Let's use, if I asked you what's the oxidation number of hydrogen here, what would you say? It's +1, because it's always +1. This is +1. We'll get back to chloride here in a minute. If I did this, what's the oxidation number of oxygen? It's -2. We just memorize it, and it's always this way. If I put this, water, oxygen, what's the oxidation number? -2. What's the oxidation number of hydrogen? +1. I'm going to draw this one out real quick. Right? So that means that this is +1, this is +1, and this is -2. All right? So that's rule number 1. Rule number 2, pure elements. Anything we see on the periodic table in its elemental state, how it naturally occurs. And for diatomics, right, have no fear, ice cold beer, hydrogen, right, fluoride, nitrogen, oxygen, phosphorus, right. All of our diatomics naturally occur. So this is a diatomic. This is its elemental state. So what would the oxidation number be for this? Rhymes with zero. 0, perfect, yes. So here, oxidation number of any pure element in its elemental state is simply just 0. If I put, how about copper, solid, what's the oxidation number here? 0. How about silver? What's the oxidation number for silver? 0. How about bromine, the diatomic? 0. All right. This one kind of throws people off here, but this is a diatomic. What is it? 0. Well, why is this one 0, but this one is +1? Well, if we take a look at this hydrogen bonded to this hydrogen, this is a molecule all by itself. It's not in a compound. This is a pure element. It's by itself. Even though it's bonded to another hydrogen, still the molecule of a same single element, and it's 0. Is this hydrogen bonded to this hydrogen? No. This isn't a compound, right? This is a molecule with 2 different elements +1. But if it's by itself, so if I do this, is this -2 or is it 0? 0, because it's by itself. So this becomes 0. So now we have 2 of these memorized, right? So rule number 1, hydrogen +1, oxygen is -2. But if it's a diatomic or some other element in its natural state, elemental state, it's 0. But before we move on, I'm going to add one more thing. What if I don't put the S here? What if I just put it like this? Still 0, yeah. It doesn't matter, it's still 0. It's by itself. Right? It's simply just by itself. Whether it says solid, liquid, gas, like it doesn't just by itself, 0. Rule number 3. Group 1 is always going to be +1. Group 2 is +2. Group 3 +3. Oh, no, I'm sorry. Group 1, group 2, group 7. I'm sorry. Group 1 plus 1, group 2 plus 3. There's only aluminum, and we're not going to worry about it in group 3. But group 7 is our halogens. Fluoride, chloride, bromide, iodide, right? Those are always going to be minus 1. So here, plus 1, chloride would be minus 1 because it's in group 7. Calcium is in group 2, so what's the oxidation number? Plus 2. If I put lithium bromide, well, lithium is in group 1, plus 1. Bromide is in what group? 7. This is minus 1. Right? So we have those rules there for groups 1, 2, and 7. Monatomic ions. Mono meaning one atom ions. I'm going to leave these here. This is Cu, 1 plus, and this is silver, 1 plus. And let's use another one here. Let's use iron, 3 plus. These are what we consider monatomic ions. They're elements that are by themselves, monatomic, and it has a charge. It's an ion. Is this an ion? Do you see a charge on it? No. Is it an ion? No. Right? Is this an ion? No. Is this an ion? Yes. This is a monatomic ion. Okay? Monatomic ion because it's by itself and it has a charge. Whatever the charge is on a monatomic ion, that's the oxidation number. So we see a monatomic ion by itself. Whatever that charge is, that's going to be the oxidation number. Rule number 5 is that the oxidation numbers in a neutral compound, the oxidation numbers in a neutral compound, is this neutral? Yes. Magnesium is 2 plus, and actually let me change this to oxygen because we already know what oxygen is. Or actually, no, let's go back to sulfide. We're fine. We're good. So magnesium sulfide. And I'm also going to put, let's use magnesium oxide. So we'll start with magnesium oxide first. Oxygen, what's our rule for oxygen? It's always minus 2. Magnesium is in group 2, plus 2. And when you add these up, they have to equal 0, right? That's because this is neutral. If this is neutral, what does it have to equal? 0. I don't know what sulfide is. There's no rule for sulfide. Right? Rule number 1, no, doesn't happen. This is not a diatomic. It's not by itself. That doesn't apply. It's not in group 1. It's not in group 2. It's not in group 7. So that doesn't apply. There's no charge on it. That doesn't apply. So we have to use rule number 5 in order to figure out what this oxidation number is. I know what this one is. It's in group 2. So it must be plus 2. Now I'm going to use rule number 5. What's the oxidation number for sulfur? Minus 2. So now let's do some more. Let's work with nitrogen and different forms of nitrogen. We're going to use these rules in order to determine. What that is. I have a really long lecture today. I apologize for that, but we got to get through this. Nitrogen. All right. I'm going to use N2. Let's go with NO3, N2H2, NH3. All right, so I have 4 different scenarios here for nitrogen. So nitrogen, what rule could we apply for nitrogen? 2. right? This is a diatomic, so what's the oxidation number here? 0. Did I have to go to the periodic table? No, absolutely did. Now I need the oxidation number. This isn't a diatomic. This is not nitrate. This is what nitrate looks like. What's the difference here and here? The charge, right? This is nitrogen trioxide. This is nitrate, the polyatomic ion, because I see the negative charge there. And we actually probably should do that one as well, but we'll do that one last. Okay. I know what oxygen is. What's the rule for oxygen? -2. So now we need rule number 5 for this. There's 3 oxygens. What's the total oxidation number? -6. So what would the oxidation number of nitrogen then have to be? +6. Right? Hydrogen here is +1, but there's 2 of them. There's 2 nitrogens. What's the oxidation number of each individual one? What was that? -1. Hydrogen here, this is +1, but there's 3 of them. So what's the oxidation number of nitrogen here? Now, these are oxidation numbers. I'm not asking for the charge of nitrogen. Right? We didn't use the periodic table to find any of these oxidation numbers. In this one, nitrogen's -3, here it's -1, here it's +6, here it's 0. So nitrogen can have different oxidation numbers if it's in some redox reaction. Right? Is that we can shift around these electrons and we get some different oxidation number. But the only way to determine those oxidation numbers is by using these rules. Right? Not once did we go to the periodic table to find out what any of these are. Right? This one here's a special case here. If we go back and revisit these, this one and this one. Rule number 5, oxidation in neutral compounds. Is this compound neutral? So what is the oxidation number for this neutral compound? 0. 0 is the oxidation number for the compound. I know this is -2, I know this is +6, but this is 0. Whatever this is, plus whatever this is, has to equal 0. In a polyatomic ion, the oxidation numbers, whatever the oxidation number is for nitrogen, plus whatever the oxidation number is for oxygen, has to equal the polyatomic charge, -1. What's the oxidation number of oxygen? Don't say -1. It's rule number, so this is -2. So what's the total oxidation number? -6. There's only one nitrogen. What does the oxidation number have to be here so that it's -1? +5. Let's do one more. Let's do phosphate. And I put the charge kind of way out here, just to not throw us off. What's the oxidation number of oxygen? -2. What's the total oxidation number? -8. And when I add this oxidation and this one, what do they have to equal? They have to equal the charge. They have to equal -3. So what's the oxidation number of phosphorus? +5. Yes. -2 times 4 is -8. So here, -2 times 3 is -6. So in order to solve these, we need to know the whole oxidation number, the total oxidation number. But that's how we get the -6 here. This is how we get the -8 here. If we were to do, so this is nitrite. We know oxygen, using rule number 1, is -2. What's the total oxidation number, Montalene, for oxygen? No, we look over here. For oxidation numbers, we look over here. If we know the oxidation number for oxygen is -2, and there's 2 oxygens, what's the oxidation number for oxygen? The total oxidation number. Not just 4, but -4. So it's -4. Now, whatever this is, plus -4 has to equal. So what is the oxidation number for nitrogen? +3. Okay? Does that help a little bit? Great. All right. Let's look at some reactions. I'm gonna grab a homework problem. So our homework problem, let's go redox reaction 4, CO3O. All right, let's do this reaction here. And we'll say, what do we have here? We have carbon dioxide. And we're going to get some Yep. All right. Using these rules, not the periodic table, using these rules here, what's the oxidation number of oxygen? -2. The carbon, can we use rule number 1 for this? Rule number 2? Rule number 3? Is this in group 1, 2, or 7? No. So we have to use rule number, it's not an ion, it's not a monatomic ion, so we have to use rule number 5. If I know this is -2, carbon has to be +2. What's the oxidation number for oxygen by itself here? Oxygen here is also -2, but this time there's 2 of them, which means this is -4. What's the oxidation number of carbon? +4. So now as we look at this, we're going to kind of break this down a little bit more. Is that carbon went from +2 to carbon +4. And oxygen went from 0 to oxygen -2. And if we're looking specifically at the reactants, and I ask you which one of these is reduced and oxidized, I want you to look for the one that's reduced first, because we're looking at the oxidation number. Which one of these did the oxidation number get smaller? What was that? Did it get smaller from here to here, or did it get smaller from here to here? So oxygen. So the oxygen got smaller, so this oxygen here was reduced, that it gained electrons from the carbon. And this carbon was then oxidized, so this had a loss of electrons. So oxidized, it lost electrons, reduced, it gained electrons. It became more negative. If electrons are negatively charged, oxidation is a loss of electrons. This is losing negative charge. That's why it's becoming more positive, because it has less negative charge on it. So differences between, but we can break down reactions like this in order to determine what was oxidized and reduced here. We look at this one here, right? Zinc, this is 0. This is in group 7, so it's minus, and these numbers should be switched around. It should be -1, this should be +2. This is -1, +2 in copper here. So we see that zinc went from 0 to +2. Chloride went from -1 to 0. Right? So here, copper went from 2 plus to 0, not chloride. So copper went from 2 plus to 0. Zinc went from 0 to 2 plus. The one that's reduced is the one that got smaller. 0 is less than 2. The copper was reduced. Zinc went from 0 to 2 plus. This was oxidized. Right? So we just kind of have those terms that we need to memorize and understand. And more reactions, endothermic, exothermic reactions. Endothermic, exothermic reactions. Exothermic reactions is some kind of release of energy, release of heat. Okay? And energy here, heat. We learned that kcals was a unit of heat in Unit 1. So anything that makes heat, right, those are exothermic reactions. And you're always going to find for exothermic reactions, the product side is where we put that energy, where we put that heat. Okay? So exothermic reactions will produce heat. And that's what we see in this case over here. Right? So we have some explosion, right? Something explodes, you feel that heat on you, right? There's fireworks, whatever it is that you can feel that heat. And even a fire. Fire is an exothermic reaction. There's some release of heat there. And then endothermic reactions is just the opposite. So notice where the energy is here. The energy is on as a reactant. Is that this requires heat. This absorbs heat. Okay? And we're always going to find in endothermic reactions that the energy is going to be on that side of the reaction area. I think the best example of these are those instant ice packs. Right? Is that we kind of crush them up, crack them, and then all of a sudden it gets instantly cold. Is that what it's doing is it's using the heat directly around it. It's absorbing that heat. It's using that heat, and it's using it up. And this is why it turns cold, right? It's because it's using that heat. It's not producing heat. It takes heat for that reaction to move forward. And in that direct vicinity, it's just using all of that heat there in order to make that reaction go forward. So exothermic, endothermic. What you'll want to do, just memorize the placement of that energy. Whether it's joules, calories, kcals. Product side, exothermic reaction. Reactant side, endothermic reaction. And we've already gone over I'm not going to revisit this. We have the single, reversible, irreversible reactions here. Is that we need to get into something we call stoichiometry. So stoichiometry, this involves using the coefficients in our balanced reaction. Stoichiometry doesn't work unless the reaction is balanced. But we are able to, very early in this lecture, we learned to convert grams to moles, moles to grams. Right? We use the periodic table. We convert something into grams per mole or moles per gram. Right? We can go back and forth. So now this stoichiometry that we're going to learn is we're going to learn, now that we know about chemical reactions, we're going to be able to convert not just grams into moles, but we're going to take some reactant and convert it into grams and moles of a product, or vice versa. Take grams and moles of a product and convert it into grams or moles of some reactant. So here's our first problem here. It says calculate how many moles of iron are produced from 1.8 moles of carbon monoxide. So how many moles of iron, this is iron oxide, right? Iron 3 oxide, this is carbon dioxide. So in this reaction, how many moles of iron are produced if we only have 1.8 moles of carbon dioxide? So what piece of information do we start with? Just what we see there, the 1.8 moles of carbon monoxide. And if you're like me and you have a little OCD, you don't have to put the 1 under it, but man, it really keeps my inner self from screaming at me when we do that. All right, so we start with this information here. The next piece of information, you're only going to get the next piece of information from the chemical reaction. We have to go from moles of this to moles of this. And in this reaction here, if I were to ask you, how many moles of carbon, or sorry, how many moles of carbon monoxide are in the reaction? How many? What is it? I can't hear. 3. Perfect. How many moles of iron are there? 2. Right. That's a definition. We've done these definitions in the just in this lecture here, where we can say that for every 2 moles of iron, there are 3 moles of carbon monoxide. And I can turn this into a conversion factor. I can say for every 2 moles of iron, we have 3 moles carbon monoxide, or I can write it as 3 moles carbon monoxide for every 2 moles of iron. These are what we call molar ratios. So these are molar ratios. It's not the only one I can write. I can write plenty more. For every 1 mole of iron 3 oxide, there's 3 moles of carbon monoxide. For every 3 moles of carbon dioxide, there's 3 moles of carbon monoxide. For every 2 moles of iron, there's 3 moles of carbon dioxide produced. And we get a whole bunch of different molar ratios. But specifically what we're talking about here is moles of iron and moles of carbon monoxide. So we're going to use that molar ratio, right? This is a mole ratio, molar ratio, mole ratio. The only place, you're only going to get that in one place, and that's in the balanced reaction. Right? It's the only place you're going to get it. You're not going to get it anywhere else. Is that this piece of information, for us to go from moles of carbon monoxide to moles of anything else, we need the chemical reaction. If I want to know how many moles of iron oxide it's going to take, well, there's 1 of these for every 3 of these, right? There's different ones, but for this one specifically, there's nowhere else we're going to get it except for that balanced reaction. So we can use that now. And we set that up, and we see that this unit here is going to cancel out this unit here, moles of carbon monoxide. And we can answer the question, and we'll get 1.20 moles of iron. So for every 1 mole, for 1.8 moles of carbon monoxide, we're going to make 1.2 moles of iron. But we got to increase the difficulty. This one's not asking us moles anymore. It's asking us grams. So here, calculate how many moles of iron 3 oxide are needed. How much of this do we need in order to make 66 grams of carbon dioxide? How much iron 3 oxide are we going to need in order to make 66 grams of carbon dioxide? So we're going to start with the 66.0 grams of carbon dioxide. Now, we have to convert this into moles. Where would we possibly find information that's going to give us help to convert those grams into moles? Yeah, periodic table, right? Periodic table is that we can get the mass of this. So if we go to carbon dioxide, if we go to the periodic table, we have carbon, oxygen, there's 1 carbon, there's 2 oxygens. Carbon is 12.01, oxygen 16.00, 12.01 plus 32.00, 44.01, 44.01 grams of CO2 for every mole of CO2. As we're learning this, I'm going to give you a tip, and I would write out both of these until you're really comfortable. I would write this, and I would take an extra 5 seconds and write this. You can see it very clearly which one you're going to need, but my suggestion is just write both of them out. It's going to take an extra 5 seconds to do so. Once you're comfortable in doing these, you don't need to do that anymore. But for now, I think we should. So which one of those should we use? In order to convert this into moles, should I use the one on the right or the left?
Right.
I need this one over here. So if we use that one over there, we can see that those units are going to cancel out. Grams of CO2 cancels out grams of CO2. And whatever our answer is, would be in moles of CO2. But it's not asking us for moles of CO2. It's asking us for moles of iron trioxide. In order to convert this substance into information of another substance, we need our mole ratio. Where do we get our mole ratio? From the chemical reaction. For every 1 mole of iron oxide, we need 3 moles of CO2. And this is the only way to do that. We can't get that information anywhere else except for the balanced equation. This unit cancels this unit cancels this unit, and we're left with just moles of iron trioxide, 0.0500 moles of iron 3 oxide, right? But again, really important that this is only going to come from the reaction up here. You're not going to find this information anywhere else. You can't look on the periodic table. It's not going to happen. The only way to get that is from the chemical reaction. Periodic table, that's to get molar mass, right? Grams per mole, moles per gram. Right? That's the information that we get there. All right. How many grams? So this, we have to go from grams to grams now. So in order to go from grams to grams, I need to convert this from one substance to another substance. So I'm going to need my mole ratio, which means that we're going to need moles, which means that I have to convert grams into moles. So we'll first start with the grams of CO. We're going to go to the periodic table. Carbon, 12.01, oxygen, 16.00, 32.0, no, 28.01. Yes? This is Thursday. You're not in this section? No.
So it's like, what?
Sorry.
All right, sorry, bye-bye.
All right. So continuing, here's this information came from the periodic table, but we had to use the reciprocal value here, 28.01. And just so that we're clear and not confused about where that came from, carbon, oxygen, 12.01, 16.00, 28.01, so we write 28.01 grams of carbon monoxide for every mole carbon monoxide. And then the reciprocal value here, mole carbon monoxide over 28.01 grams carbon monoxide. And we needed to use this form here. But now that we have moles, right, because those units are going to cancel now, and now we have moles left, now we can use that mole ratio because now we're in moles. Can't use it unless we're in moles. So the mole ratio between iron and carbon monoxide. 2 moles of iron for every 3 moles carbon monoxide. For every 2 moles of iron, 3 moles of carbon monoxide, and we can cancel the units out. Cancel those units. We're almost there. It wants grams, and we have moles. Where do we get that information? Periodic table. We get the molar mass, 55.85 grams per mole, and we use that information to finally convert it into grams. Right. This comes from the periodic table. This comes from the periodic table. This is the starting information. And where does this information come from?
Equation.
The equation, right? This comes from the equation up above, right? So that's where we get that piece of information. All right. On to our last topic. Our last topic is going to be ideal gas law and some other gas laws. So we're almost there. Then we'll get into our lab, and the lab will go pretty quick, actually. It's not a lengthy lab at all. So plenty of time still. All right, ideal gas law. So you do need to memorize this formula here. For gas law. So PV equals nRT is what most people say, the ideal gas law. P stands for pressure, V is for volume, N is for the number of moles, R is a gas rate constant, and T is for temperature. Now, the units we need here, right? Temperature has to be in Kelvin for this formula to work. If it's in Fahrenheit, you have to calculate it, convert it into Kelvin. If it's in Celsius, we need to convert it into Kelvin. Okay? Units of gas have to be in liters for us to use this formula. If it's in milliliters, we have to convert it to liters. Here, pressure is going to be in units of atmospheres, torrs, millimeters of mercury. And then we have this definition here. 1 atmosphere equals 700 millimeters of mercury. So 1 atmosphere, if you're standing at the beach, toes in the water, you are at 1 atmosphere. Okay? But as you go up in elevation, right, that atmosphere decreases. As you go down in the water, that atmospheric pressure will increase. But the other units here, mmHg translates to millimeters of mercury. And that's also pressure. So over here we have this barometer. In the safety lecture, Britt noted that there was mercury in here. And as pressure increases, it pushes down on that mercury, and it pushes the mercury up to 2. And if it decreases in that container down here, right? Not so much pressure so that this can go down, but we can read millimeters of mercury here. So if I wanted to know the atmospheric pressure and up here at the college, well, I can read this as 692.8. So it is 692.8 millimeters of mercury. And luckily for us, we have this definition here that for every 1 atmosphere, there are 760 millimeters of mercury. This cancels this, and we can calculate this at 692.8 divided by 760. 0.912, 0.91, what was it, 0.9116. So up here, we're not at sea level, right? We're 4,000 feet up, and we are less than 1 because as we go up in elevation, we do lose a little atmospheric pressure. So we're at 0.9116 atmospheres here in this particular room. So how do we use this here, right? We're just given problems, and sometimes we need to rearrange the formula. Sometimes we need to put a little algebra in here, but we'll get through all our information here. So calculate the volume. So let me just write this first here. So this is PV equals nRT, and we're asked to find the volume of this. So calculate the volume occupied by 2 moles of an ideal gas. N is equal to the number of moles. So that's 2.5 moles. Right? That's what N equals. If we go back up here, we see that N equals the number of moles of gas, and the problem gives us the number of moles of gas. It says the temperature is equal to 15 degrees Celsius, but we need this in Kelvin. So 273.15 plus 15 is going to equal 288.15 Kelvin. So now we have the temperature in Kelvin. The rate constant, I didn't go over the rate constant, but let's kind of, this value will never change for the gas constant. This is the reason why we have to convert everything, is because in order to use this as liter atmospheres over mole Kelvin. So all the units have to be there in order for, if we don't convert all the units, we can't use this gas constant. So we know what R is. So in this next equation, so R is equal to 0.8206 liter atmospheres mole Kelvin. And it does say, it gives us a pressure. Our pressure is equal to 0.75 atmospheres. And it's asking us, under these conditions here, if the temperature is 288 Kelvin, and there's 2.5 moles of some gas in there, and the pressure of that container is 0.75, what's the volume of that container? And we can figure that out. So this has to be rearranged. Just takes a little bit of algebra. If I divide this side by P, this goes away, but I have to do the same thing over here. So volume is equal to nRT over P. That's just a simple, some little algebra work that we have to do. But we can plug in all of our values now. So we have 2.5 moles times 0.08206 liter atmospheres mole Kelvin times 288.15 Kelvin over 0.75 atmospheres. Might look a little scary, but we're going to cancel some units out right now. Moles cancels moles. Atmospheres cancels atmospheres. Kelvin cancels Kelvin. The only one that's left is liters, and that's definitely a unit of volume. So 2.5 times, that's 12, 2.5 times 0.08206 times 288.15 divided by 0.75 equals a bunch of numbers. 4 sig figs, 2 sig figs, 2 sig figs. I'm going to round this to 2 significant figures, and we get equals 79 liters. Okay, so here's our setup. we can see that all those units cancel out, and we do in fact get 79 liters. So using that formula, right, we just need to rearrange it. If it's asking for pressure, rearrange it for pressure. If it's asking for temperature, rearrange it so you see temperature. But this is pretty specific. We're just asking for some information about some gas that's sitting in some container. Right? If I give you the volume, temperature, the number of moles, what's the pressure of that container? If I give you the pressure, the temperature, can you tell me how many moles of gas are in that particular container, right? And we can figure those out by just rearranging that. So that's what we call the ideal gas law. There's some other gas laws that we need to know. This is the first one. This is called Boyle's law. Boyle's law is an inverse relationship between volume and pressure. If one goes up, the other goes down. That's an inverse relationship. Pressure goes up, volume goes down. Pressure goes down, volume goes up. And we can see that here. And this happens, notice the temperature doesn't change here. So this is done at constant temperature, right? But here, going 2 atmospheres, if we increase the volume, increase the pressure, decrease the pressure, I'll get this. Decrease the pressure, the volume goes up. That's our inverse relationship, right? And here, and we can actually do it the other way around. Volume here is going to decrease, but the pressure increases, right? If pressure increases, volume decreases, and we can talk about it both ways. If pressure increases, volume decreases, right? We go from 1 to 2, pressure increases, but the volume's going to decrease. If we go this direction, if our pressure decreases, volume increases. So this is Boyle's law, and how we write this is Boyle's law. Instead of doing this, initial, final, this means the same thing here, but we're just going to use numbers instead. Initial pressure, and initial volume, final pressure, final volume, but we don't do that. We just write it as 1 and 2. So initial pressure, initial volume, final pressure, final volume. If my initial pressure is 6 atmospheres and my initial volume, all right, if our initial pressure is 6 atmospheres and our initial volume is 2 liters, and let's say our final pressure is 3 atmospheres. Well, what's the final volume? If I take this and I decrease the pressure to 3 atmospheres, what's the volume of that gas now? Well, 6 times 2 is 12, so what 3 times some volume also has to equal 12, right? This value has to equal this value. So what's our, for the final volume is going to be 4 liters, and that makes sense. Decrease the pressure, I have to increase the volume. Right? So there's an inverse relationship between volume and pressure. The next one is what we call Charles' law. Charles' law is done at constant temperature, or pressure here, constant pressure, so the pressure doesn't change, right? This is a direct relationship, okay? Lower the temperature, we lower the volume. Increase the temperature, we increase the volume. Right? But higher temperature, higher volume, lower temperature, lower volume, and this is Charles' law, and it's a direct relationship. Direct relationships are written a little bit differently. So here for Charles' law, we're going to say V1 over T1 is equal to V2 over T2. Direct relationship. The other one was an inverse relationship between pressure and volume. This is a direct relationship between volume and temperature. Then we have Avogadro's law. This one is, I think this one's pretty obvious. You know, if we increase, and this is done here, yeah. So here, if we increase the number of moles, we increase the volume. And that only makes sense. Like I have X amount of moles of coffee here. If I decrease the number of moles, well, I just decrease the amount of coffee that's in there. So that one's just kind of pretty obvious, right? But this is a direct relationship between volume and the number of moles, right? Increase the number of moles, I increase the volume, decrease it, we decrease the volume. So the last one we have is just kind of the combined gas one. You can do one of two things. You can memorize all four of them, or you can just memorize one. To me, it doesn't really matter which one you do. But I will show you how to just use the one. I'm preferable to just using one. This is the one that I just use here, P1 V1 over T1 N1 is equal to T2 V2 over T2 N2. So this usually does everything for us, okay? You can memorize. I won't. The exam's not going to ask you which one of these is Charles, which one of these is Boyle's law. It's just going to ask you to make some calculations. Okay, so it's not really specific. So this is why this one works out, because I'm not specifically asking you which law is this. So if we take a look at some of these here, it says a balloon with a volume of 2 liters is filled with the gas at 3 atmospheres. If the pressure is reduced to 0.5 atmospheres, what would be the volume of the final of the balloon? How do you know whether to use this or this? Right? You're looking for keywords here. For this here, for Boyle's law, for Charles' law, for Avogadro's law, something happened to the gas. We changed it somehow. I increased the number of moles, I decreased the pressure, I increased the temperature, and what was the effect of that? Right here. What was the final pressure? What was the initial temperature? And we're always just kind of looking for keywords here. If the pressure's reduced, it was 3 atmospheres, P1, and we reduced it to 0.5 atmospheres, that would be P2. And here, in this one, we're just asking you information about some gas that we're not changing. This is the information about the gas. Tell me something about the volume. There's no change. I didn't decrease, increase, change anything. And that's kind of how we know which one to use, is we're again looking for keywords here. So here, if I'm holding a balloon, let's go P1, I have B1, I have P2, and I have B2. A balloon with a volume, if I'm holding a balloon that has 2.0 liters of helium in it, is that my initial volume or my final volume? Initial, so I'm holding it. The balloon has 2.0 liters of some gas. If I'm sitting with the balloon at 3 atmospheres, is that initial or final pressure? I'm sitting with it at 3 atmospheres. If I'm going to reduce it to 0.5 atmospheres, what is the volume of the balloon? Now, how do we take this and fill it up with this? Right? We're going to get rid of stuff here. Did it talk about the temperature at any time? Guess we don't need it. Did it talk about the number of moles that we have? No. Don't need that either. Which means this is what I need here. I need this. I need P1 V1 equals P2 V2, and we're specifically asked to find V2. I'm going to do a little math here. P2, P2, these cancel out, so P1 V1 over P2 is equal to V2, and now I can solve this problem. P1, 3 atmospheres, times V1, 2.0 liters, over P2, 0.5 atmospheres. This unit cancels this unit. So 3 times 2 is 6. What's 6 divided by 0.5? Please don't say 3. All right, do the math. What is this? 3 times 2 divided by 0.5? 12. 12 liters. The significant figures here are off. I think it should have said 0.50. Should have said 3.0 atmosphere. So let me fix that because that kind of throws everything off here. So this kind of should be 3.0 and this should be 5.0. That way we can stay with 2 significant figures here. All right, let's do another one here. Let me reset this problem up here. T1, N1, T2, N2. All right. 600 milliliter sample of nitrogen is heated from 27 to 77. What's the final volume? Did it talk about the number of moles? Don't need that. Did it talk about temperature? Yes, so I need that. Did it talk about volume? Yes. Did it talk about pressure? No. So I don't need this one and I don't need this one. So I have V1 T1 is equal to V2 T2. Well, if I have this sample that's 600 milliliters in volume, is that my initial or final volume? Initial. Initial is going to be 600 milliliters. And let's get our temperature here. It goes from 27 degrees. So I start at 27 and I end at 77. What's my initial temperature? 27 degrees Celsius. And our final temperature, 77 degrees Celsius. Right? This has to be in Kelvin. Has to be in Kelvin. The reason this has to be in Kelvin is Kelvin can't go to 0. Or we don't have anything that hits 0 Kelvin. But Celsius, Fahrenheit can go 0. Put in your calculator 1 divided by 0. 1 divided by 0 in your calculator, and when your calculator stops laughing at you, please let me know. All right? We can't divide by 0. We can do 0 divide by 1, but I can't do 1 divide by 0. So if this is 0, then there's an issue trying to solve this, right? So we convert this to Kelvin. So 273. I'm just going to simplify it. I'm not going to put the 0.15. I'm just going to simplify it. Plus 27. Get 300, and then here 273 plus 77 is we're going to get 300. All right. So we have our temperatures here. What's the final volume? Again, we have to do some algebra work. If I multiply this by T2, I'm going to multiply this by T2. This cancels this. And our new formula becomes T2 V1 over T1 is equal to V2. All right, so now we're just going to stick everything into the problem. So we have 350 Kelvin times initial volume 600 milliliters over initial temperature 300 Kelvin. Kelvin cancels Kelvin, and whatever our answer is in milliliters. All right, so Can somebody give me the answer to this? 350, what is our answer here? So 700 milliliters, does that make sense? If we increase the temperature, volume also increases, so that absolutely makes sense. Right. Okay, yeah, I think we're good. Sorry about going over like that. That was a really long lecture. But again, this is the longest unit we have in the textbook. I don't understand why it's so long. But let's take a break for at least 15 minutes. We'll come back at, let's say, 12:20. 12:20, I will explain the lab. We'll get through it rather quickly. It's not a lengthy lab, and then you guys are free to go after that. But let's go ahead and take a break.